Hi, this is Miss Litton, and this is my wonderful Period 1 class. Say hi. Hi. And we're continuing on in this presentation. We're going to focus on the science practices. So there are 7 science practices. And along with the next generation science standards, I love this change. Because I'm going to tell you, it used to be just like memorize every single fact and somehow that made you a scientist, but you and I both know that's not true. Now the approach is to act like a scientist. And to act like a scientist, you need to know these 7 science practices. These are the 7 you've been going through and will be going through on your homework, so you kind of get an idea about all 7. Okay, so I'm going to walk you through that. I actually ping pong back and forth. Did we talk about how to ping pong? Okay, so slate, you're going to take all the odds. Blue, you're going to take all the evens. Go.
Presentations and models to communicate scientific phenomena and solve scientific problems.
Are they listed in your group shared notes too, right? Guys, they're on your group shared notes too, right?
Okay, whatever. The student can engage in scientific questioning to extend thinking or to guide investigations within the context of the
Okay, go quicker. I want to take over. I just want to expose you to them a little bit. All right, now, sorry if you're not done, but I want to just hit these real quick with you. Number 1 is you're communicating with models. Did you already have an ed puzzle on that?
Yeah.
Yes, you did. And number 2, you're using, does anybody know what that word is? Math. Math appropriately to analyze data, probability, and genetics. And you have an equation sheet, okay, and I'll talk about that in just a minute, that you can use during the AP exam, and you want to be familiar with that equation sheet. We'll be using it the entire year, okay? And I'll show you one of those equations today. Number 3, you want to questioning scientifically. Number 4 is collecting what? Data. Good. Number 5 is analyzing and, any guesses? Close, evaluating. Nice. Analyzing and evaluating data. Number 6, justifying conclusions and theories. Evidence to support a claim. Evidence to support a claim. Remember on all your labs, it goes claim, then what? Evidence, reason. Good. Evidence to support a claim. And number 7, expanding understanding and connections. So we'll be looking at the 4 big ideas that we already talked about. Okay, Blue tells Slate, just give him this quote and explain it to him. Go ahead. So much insight right there, just a few words. Okay, so the thing about science is it's not once and done, okay? It gets done again and again and again by some other scientists who do it again and again and again, by some other scientists who do it again and again and again, and it continues to get refined until you have some consensus on an idea, and then you might have a theory. Okay, so if you look here at the top, it's talking about making observations and thinking about questions, formulating a hypothesis, coming up with some experiment, get some data, refine, try some other hypothesis, go again, and over time you could develop that theory. If you look right here, there are 2 types of reasoning. Inductive reasoning and deductive reasoning. Inductive and deductive. Oldest bio buddy, you take on inductive reasoning. Oldest bio buddy, youngest bio, young, you do deductive reasoning. Go ahead.
Deductive reasoning is about a general process, specific results are the big
right in front of your face, and you have your face, or you can that you can.
All right, and go into your notes where it says the process of science. The scientific method acts as a guideline for scientific studies. You make an observation, a formal way of seeing what happens, a hypothesis using inductive reasoning to formulate a possible explanation for a natural event. Using inductive reasoning to formulate a possible explanation for a natural event. So you're getting from here, and coming up with some general conclusion like, this is how I think it's going to work. Yes?
But hypothesis was a possible explanation for a natural event?
Yes. Okay? And then always ask somebody near you before you ask me, just in case they already have it. Okay? Then for predictions here, you're going to use your deductive reasoning. Deductive reasoning involves if-then logic to make a prediction. You're like, okay, so now I have this inductive, this is how I think it works. This is my general idea. I'm using my inductive reasoning. Then I'm going to deduce from that, I'm going to do this one experiment, and this is how I think it's going to turn out. Okay, so I'm making that prediction. Your experimental design, you have two types of variables. You remember these? Not it. Past or play. Quickly, independent, dependent variable. Pass or play on that. Go ahead. Okay, come back to me. Whoever just explained that, I want you to be quiet for a minute. I want the other bio buddy to explain, why did they use this diagram as a model to explain independent and dependent variables? Go ahead. Okay, now come back to me again. Does this remind you of the new flowcharts I want you to do? Input and output. Independent variable and dependent variable. Dependent data, right? Does that make sense to you? Okay, now we're going to talk about a couple of different hypotheses. This may or may not have been introduced to you. I think it got introduced to you last year in Foundations, yes? Thought I taught it in mine. Okay, so we'll talk about these two. Research hypothesis and a null hypothesis. Okay, so let me talk to you a little bit about these. Okay, research hypothesis, this is what you refer to as an H1, and you're saying A is connected to B. That would be maybe if I say, if I put pizza in one corner of the room, then more students will go towards the pizza because they are hungry. Did you follow that? I'm saying A is connected to B. I'm saying the conglomeration of students is connected to where the pizza is located. A is connected to B. Okay? That is a research hypothesis. A null hypothesis says there is no connection. A null hypothesis says there's no connection between where the students are and where the pizza is. Now, if we collect the data and we say there are 30 kids in this room, 25 kids are near the pizza, and only 5 kids are not, and that's because they're lactose intolerant, come to find out, okay? Now, did I support my null hypothesis, or did I not support my null hypothesis? Right, and this is what science does a lot of times. Oftentimes, it's easier to disprove a null, which then would support the alternative hypothesis, right? If I say there's no connection between where students are and pizza, and we get a high amount of error, like this is significant number of students are near the pizza, now I can say where the pizza is located is, or where students are located is probably connected to the pizza, right? And this is a real obvious one. But if I say to you something like, I think students who get more, if you get more sleep, you will get higher grades. That would be what kind of hypothesis? If you get more sleep, then you will get higher grades. That's research. But what kind of factors can affect grades? What? Tell me some things. Study time. What else?
Study method.
The class itself, how it's organized. Intelligence, how bright you are, how easy it is for you. There's a lot of things. So maybe I don't want to write a hypothesis like that. What kind of hypothesis might I want to write? No. There is no connection between the amount of hours you sleep and your grades. Now all I have to do is get your grades and get your hours, right, that you sleep. And if there's significant numbers of students, if it comes up like it doesn't really support that null hypothesis, if it doesn't support the null, then it probably supports the research. So I can't say that it's a direct connection, but I can say this. I can say sleep does seem to have an impact on grades. Do you see that? By disproving the null. It's easier to disprove a null than to have really good evidence for something that has other factors that are involved, other variables involved. Does that make sense? In your own words, you can use these, but try to put it in your own words. What I just did, youngest bio buddy. Explain it to your oldest bio buddy. What's the difference between a research hypothesis and a null hypothesis? Go ahead, bless you. Boom shakalaka?
It's just like a random thing, you know.
Okay, now, so take a look at this. I've added to the model we just had. Whoever was the model explainer last time, don't be. I want the other bio buddy. How have I changed this model a little bit to help you understand this concept? Go ahead.
So it's changed because it shows that how the independent is independent with the research hypothesis, but it says there's no connection between independent
Can a null hypothesis be useful? Yeah, because you can start ruling some things out as either a contributing factor and not contributing factor. Does that make sense? So null hypotheses are very useful, okay? So are research hypotheses, but I would say predominantly you see a lot of null hypotheses. So here we go. Question, is there a connection between the amount of sleep you get in your grades? Discuss with your bio buddy. Write the HO, write the H1. H1 is research. HO, like 0, that's like null. No connection, right? So write the 2 and I'll show you the 2 I have. Go ahead. You don't have to type it. Just think it in your head. Discuss it, sorry.
Okay, so if a student gets more than 8 hours of sleep or the amount of sleep, then yeah.
I heard you. Does that make sense? All right. Now, chance. Chance is always a part of your results. Okay? Chance is always a factor. Okay? And when you do when you do a null hypothesis, it says that anything that happens, you're saying it's due to chance. So I'm saying, do you think this is due to chance if 20 of the 25 students are near the pizza? Do you think that's due to chance? Or do you think that's a statistically significant that 20 of the 25 students were near the pizza? Because if I said a null hypothesis and I said pizza doesn't make any difference to student location, but 20 of the 25 students are over by it, that sounds to me like it's statistically significant. There's actually math we can do to say whether or not it's statistically. There's an equation you'll do and you're going to do it all the time and you're going to be like, this is so easy. And it's one of your, have you done this one? ChiSquare. You did it a little bit. Didn't you do a little bit in Fox?
It was like the first.
First thing, and then we never did it again. Okay, there we go. All right. So what the null hypothesis is saying is any extra students we have over there is due to chance. But we have a line you draw on. It's 5%. Unless you're a drug company. Like, you know, when they say, when you watch a drug company commercial, they say, could have diarrhea and, you know, could spontaneously throw up. Your heart could stop, that you die, right? So theirs is less than 1% chance. Do they want any chance being a factor? But up to 5% is usually acceptable, okay? But again, not if you're a drug company. Alternate research hypothesis says it is due to the independent variable. Whatever is happening is due to the independent variable. The pizza is drawing them in, okay? So let's take a look at this. If I were to deal out 20 cards, okay? I shuffle, 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 shuffle. I deal out 20 cards. What would you predict how many I would have of each suit? So there's, oh, wait, I want to take that back. Yes, 5. Let's go each color. Let's just go each color. You would predict that 10 would be red and 10 would be black, right? Because there's only 2 colors in the deck, red and black. Do you agree with me on that? Okay, so what would be your research hypothesis? What would be your null hypothesis for that? Discuss with BioBuddy.
How many other colors just because there's 20.
Right? I'm saying that there is a connection there, and I'm predicting that there will be 10 red and 10 black. Right? I'm saying there's a connection. Okay? If I said null, if I deal out 20 cards, there will be a random number of reds and blacks. I could have 13 or 16 reds, you know, and 4 blacks. Right? So let's say this is my data. 8 were red and 12 were black. Okay? Is that significant? Is that acceptable? Is that an acceptable amount of chance? An acceptable? Now, for us, if I stick with the H1, okay, 10 will be red, 10 will be black. If that's the one I go with here, if this is my hypothesis, is that an acceptable amount of deviance from what I expected it to be? Is that okay? What if I had 13 black and 9 were red? Oh wait, would that work? And 7 were red. I got an extra card. Do you see what I mean? Where do you draw the line where you say this data, something's wrong? Maybe I didn't shuffle the cards before I dealt them out, right? I would look to see if there were errors in my experiment. Did I set the experiment up wrong to begin with, or did I just open up a pack? Or, you know, what could I have lost some of the cards? I need to look and I need to investigate that. So let's talk about this. I observe 8 and I observe 12. What should it have been? 10 and 10. And I think if you had whatever teacher you had, I gave them this. Did you do this last year?
Yeah, I think so.
Some of you might have done it because I gave them this presentation. Okay, so what was the difference in red? 2. What was the difference in black?
2.
Yeah, 2. And you know what? That's always going to be the same number when you only have 2 choices. Because if it's not this, it's this, right? Right? If I had 3 choices, then that number could change. Now, this was a difference. I had 2 more than I should have, right? So this would be like a plus 2? Yeah. Okay. And over here I have what? I'm under 2, right? Now,
Wait, no, switch.
Oh, yeah, you're right. You're right, and I'm wrong. Thank you, scientists. So now, all you have to do to analyze, you take your difference and you square it. When we square it, it won't make any difference if it's plus or minus anymore, right? So what is 2 squared? 4. Okay? And 2 squared? 4. Okay? And your next step is you square your difference and you put it over what was expected. Okay, 10. Good. So come right here, observe minus expected squared over your expected. You need to do that for both the red and for the black. Take a piece of paper, take a calculator. If you don't have a calculator, look, in the back of the room, I have calculators. When you take your AP exam, you are allowed to have a 5-function calculator. So only use a 5-function calculator when you're in here. Do not use one of your big ones. You can get yourself a 5-function calculator at the dollar store. Okay? You want to have a square root and a square. If it's a 6-function, they'll take that as well. But you can always use these when you're in my classroom. But I would just get my own. Yes? Does that look like it only has 5 functions? Okay. So what would be the answer to that question? No. Okay. Varsity, please. Varsity.
It was trying to get to water.
Let's go, let's go, let's go. We got a lab problem. So we already did this, right? For both of them, because we only had 2 choices. So this is easy for us. So the observed of one of them was 8, and we expected how many? 10. So it was a difference of 2. Okay? So 2 times 2 is 4. So I would just be saying 2 squared, 2 times 2 is 4, over what did I expect? 10. Okay? Plus, and it's going to be the same thing over here, right?
Yeah.
Okay? So 4 over 10. What is 4 divided by 10? 0.4 plus 0.4. You're just going to sum it all up. So 0.4 plus 0.4 equals what? 0.8. Got that? So now, think about what you did there. All you did for each category of your result is you took the deviation from what you expected, and what did you do to that deviation? Squared it, and then put it over what you expected. And then of the next piece of data that you had, deviation, squared it, put it over what you expected. And if you had more options, 3 or 4 options, you would continue to do that. Then you just take up and add them all together and you get a value. That is your ChiSquare value. There is a chart that you look on, and you will have that chart on for your AP exam, part of your equation sheet, and you will look to see, is this statistically significant or not? And that's it. And you can do that for all the results of your experiment. So take a look right here. How confident are you? I want to be 95% confident. If I'm in a drug study, I don't want to kill people who take my drug. Maybe my confidence value needs to be 99% confident. Are you with me on that? Okay, so usually the critical value is about 5%. If it falls up in there, we have some concern. So take a look. Here is the full chart. What you will get when there's different ways, and I've given you a copy of this already. You have this associated with your notes. They'll give you just the ones you're concerned about. They won't give you all the other values, and they'll turn it sideways the other way. But I'm showing you the full chart right now. So the first thing you have over here is your degrees of freedom. How much freedom do I have? In this case, I only had 2 choices. So if I wasn't this, I was this, right? I was that, right? So I have 1 degree of freedom. So it's however many choices you have, minus 1. So if I had 4 results, if I was doing spades, clubs, hearts, diamonds, then how many degrees of freedom would I have? 3. Does that make sense? Because I have 4 choices. You subtract 1 off. That's where you look. So I look down here, and I go, for this case, I had red or black, subtract 1, so I'm at 1 degree of freedom. Then I just go over here, and I try to find my number. As long as I'm in here, I'm okay. Once I cross this yellow line, the 5% line, then I'm in trouble, and I need to look at my data. Okay, so for instance, as I come across here, where does our 0.8 fall? Right here, somewhere where I put the yellow star. Between 0.46 and between 1.07. So can I accept this data? Yes. So I'm all right. That is not statistically significant, and so everything is fine. If we had written a null hypothesis with a pizza, and 20 out of the 25 students we're over there, that would probably be a big old fat number on the right, and I am going to be concerned. And I'll say, this null hypothesis isn't working. It's a statistically significant number, and I need to look and see, yes, pizza does have an influence on where my students are. Okay? So you can use this either way. If you're doing a research hypothesis, you don't want to be over that. But if you're doing a null hypothesis and you're trying to show that there is a connection probably, and you're using a null and saying there's no connection, then you want to have some big high number, and then you can say, oh, it's statistically significant. It has something to do with it. Where the kids are is connected to that. Okay? So let's take a look at another example. Oh, you already know this. Youngest bio buddy, explain this right here. Go ahead.
So it's the differentiation top square over the expected value, and it is added together, and that is equal to the squares.
All right, now come back to me. This just means observed minus what? Expected squared over expected. But this means sum of. So do that for every one of your results. That's what that stands for. That just means summation. Okay? Or if you're in a fraternity, something else. Okay? But what I'm just summing that up. Every single one of my different categories of results, taking the deviation, squaring it, put it in and over what my expected value was, and I'm adding up all those deviations. Okay? And then that gives me that is equal to my chi-squared. You don't need to square root it to solve for x, okay? Chi-squared is just the way of writing the symbol of that particular test. So we don't take the square root of 0.8 and then look that up. That is our chi-squared. Now I want you to look back here again. What trend can you see as you go down in degrees of freedom? It gets what? Bigger. That's because we only had 2 options here. But if you have 3 or 4 or 5 or 6 or 7 or 8, your number is going to get bigger just because you have those. So the lenience there, right? The leniency is going to be bigger. So that makes sense. If we're here, that's okay. And you look right here, 3.84. Look, if you go down to 4 degrees of freedom, 3.84 is okay. Do you see that? Because I have more choices, so overall I'm probably going to have a bigger number that I'm adding in together. Here I was only adding in 2. Okay, so you have to make sure you're on the right degree of freedom as you go through that. What do I have here? Oh, we already went on that. Oh, here, if this helps you. Okay, this is a good fit for my data. I'm okay with it. If it's a research hypothesis, this is bad fit. I need to consider something else as being my problem. If I'm doing a null hypothesis, I probably want there to be a big old chi-square number so I can disprove my null and support my research. Yes?
What are those numbers on the top?
Which one right here? Oh, 90% confident, 80% confident. Those are your confidence levels. Okay? Now, let's take a look at this. Try this on a piece of paper. I don't know if you can do it on your Chromebook at all. So let's look at this. Currently, 35.2% of chemists are women. So I'm going to write myself a null hypothesis. Women are not underrepresented in the field of chemistry. So I want to know, I don't work for Google, if you know what I'm talking about. You know about that? Oh, yeah, engineers. If 35.2% of chemists are women, I'm saying there's no connection between the sex and who is a chemist. There's no connection. They're not underrepresented. I want to, you tell me, disprove my null or support that null. Do the math for it right now. You can do it with your bio buddy. Think about it. I'm saying women are not underrepresented. So what would I expect if they're not underrepresented? 50-50. Can you work it off that? Okay.
So would you have to solve for the guy side as well?
What do you think?
Yes.
I'm going to pause you just for a second. So is this value right here, this 35.2, my observed or my expected value? This is my observed, okay? This is observed for who? Women. So if I'm observing 35.2 for women, then what conversely must I be observing for men? 64.8. Mm-hmm. And what would I expect if there's no problem, because I'm writing a null hypothesis, no connection? What would I expect for both? 50. Okay? So hopefully you thought that part out and you got at least this far. How many degrees of freedom do we have? One. Okay, just checking. Oh, sorry, skipped ahead. Where are we? Here we go. Is this what you got? Okay. So I took the difference, I squared it, and I put it over what I expected, and I got a number. Did you get that far? Just kind of rush up. Okay, so you got your chi-squared of 8.8. I'm either a male or a female. Okay, there's another whole discussion. Okay, but for this purposes of this, okay, those identified as male, those identified as female. Okay, I have a degree of freedom then of just 1. Do you think 8.8 is going to be statistically significant? Yeah, I think so too. So if we take a look, okay, here we have 1 degree of freedom. I'm not even on the chart. It's so significant. Okay? This number right here is a really good number to memorize because that's always the cutoff point for 1 degree of freedom if you have just 2 choices. Okay? So 3.85, that right there, if you're in there, then it's going to be, I knew right away because it was above 3.85, this was going to be statistically significant. Okay? So by doing that, okay, it's statistically significant. It would come up less than 1% of the time, okay, if we did this due to chance. Chance would see those kind of results if we randomly did this again and again, generation after generation. Due to chance, that would only come up 1% of the time. So it is statistically significant. And so, yes, if I disprove my null, this leads credence to my research or alternative hypothesis, which would say that sex has an impact on the career choices, right? Because so few women are chemists. They are underrepresented in that field. All right, now, tie that up, put a bow on it, talk about it with your bio buddy, talk about research, alternative, talk about why we use the chi-square test. Go.
You're able to research it and find it. I guess it works better for just bring your data and what you're saying to show that.
Okay, and then I'm going to go ahead and close you down now. I hope that was helpful. I'm going to give you one more thing though. Okay, guys, I'm going to show you one more. We don't have time because I really need to talk to you about the lab now. But you could do this one if you wanted to. Is there a problem with my random card generator? Okay, let's count the numbers and you work it at home and we can talk about it next time. Okay, so I have 1, 2, 3, 4, 5, 6 clubs. Write this down somewhere. Put it in your notes. Practice. Okay, add it to your group shared notes. 1, 2, 3, 4, 5, 6 clubs. I have 3 hearts. I have 3 spades. And I have 1, 2, 3, 4, 5, 6, 7, 8 diamonds. Did you get that? 6 clubs, 3 hearts, 3 spades, and 8 diamonds. Okay? I know some of you, because you love to like problem solve, you want to work on that right now. Okay? But do that independently on your own. Come up with your results and then talk about it with your bio buddy, and we can address it next class if you want to do that. Okay? But that will give you a good practice problem on that one. All right? And now I want to give you something that you can use a ChiSquare test on, and that is your lab. So get out your lab as you gave a dry run of it and show it to your bio buddy. Oh, and that's the end. Have a good day. Make good choices.